Good afternoon. We are going to be covering in this video series a CSTR that is now in series. And so in the previous video series, what we did was look at a CSTR with an exothermic reaction taking place inside with a cooling jacket surrounding it, and we evaluated how the mass and energy balances were changing with respect to time, or respectively the concentration and the temperature within the CSTR. And so we're going to be using all these same parameters, but the difference now is going to be that we are dealing with 15 CSTRs in series, and so our volume is going to be the same, except now it's going to be divided by the number of individual CSTRs that we have, which is 15, and then our heat transfer coefficient is also going to be divided across the number of CSTRs that we have. The initial temperature coming in is going to be 350 Kelvin. The initial concentration, not coming in, but the initial temperature across all of our 15 CSTRs to begin with is at 350 Kelvin. Same with our concentration of A. Every CSTR is going to begin with 0.5 molars per liter for the initial conditions. Then what's going to be entering into the very first CSTR is going to be a stream at 350 Kelvin with a concentration of A with 1 mole per liter. And then with the cooling jacket still of 290 K. All the other parameters are going to be the same. And so the goal in this video is going to be to derive the time-dependent material and energy balance equations, and then simulate how the concentrations of A and temperature change and evolve over time for each of the individual CSTRs in our series. Now, usually I'd be writing this next part out as we go and as I explain it, but for some reason the technology that I usually use just for the life of me was not pairing with multiple different connection points and so on and so forth. And so I just real quick wrote this out ahead of time so I could walk through it. We're dealing with 15 CSTRs in series, and so what we're going to be seeing is the initial stream is going to be coming in on the first one, the initial conditions, and because it's an exothermic reaction, anything that enters into every subsequent CSTR is going to receive all the conditions from the CSTR just preceding it. So with the first one, the initial stream conditions, the initial feed conditions basically, so the temperature and concentration of our feed stream coming in, that's going to be what goes into the first CSTR, but all the respective ones that follow, for 2 is going to receive everything that happens at the end of 1. And then 3 is going to receive everything from 2, and so on and so forth down the line. So here I show this in this ladder thing with ladder mechanism. Everything is we're assuming perfectly mixed, and so everything that falls into the next CSTR is receiving what came before it. And so we would expect that as the reactions continue to occur over time, A continues to convert and be consumed in the reaction, and so the concentration of A should be decreasing. Because it's an exothermic reaction, the less concentration of A there is, the lower the temperature is going to be in an exothermic with the exothermic reaction that's taken place. So the temperature should decrease because our cooling jacket is receiving that steady continual supply of 290 Kelvin. And with a PFD, we have got no back mixing that is occurring. So let's go ahead and simulate what this is actually going to look like now. And so because we're using a lot of the same parameters as our previous video series with the exothermic CSTR, we can actually go ahead and take all those parameters. Well, let's go ahead and grab our tools first here, plop those in, because we're going to be using these same things. We're going to be doing our array of values. We're going to be solving, we're going to need solve IVP because we're going to be solving, in this case, 30 simultaneous differential equations, because there's 15 CSTRs, which means we've got 15 different concentrations to evaluate and 15 different temperatures to evaluate. So we'll need our solve IVP, and then of course we're going to plot this out so we can visualize everything we're trying to simulate here. Let's go ahead and grab our initial parameters. And a lot of these are fine. Volume is getting divided by N, and our heat transfer coefficient is also getting divided by N. which means we should probably specify N. And then the other difference is that the only, well here, so concentration, we need to specify that this is the initial conditions for all 15 of our CSTRs to begin with. So we're going to do N. We're giving all of our CSTRs the initial conditions and the initial temperature here. And then let's go ahead and do T end of 3 minutes instead. Let's go ahead and run this. Great. Now we've derived the equations already in our previous video series, which is that our material balance, this is the differential equation that we were able to derive based off the reaction of A over time of what's coming in versus what's coming out. And so we've got our flow over with our volume, and then concentration of A in minus the concentration of A that's left, and then minus what is the rate at which A is getting consumed. And then for our energy balance, here is the rate at which energy is entering or leaving the system per se. So the flow of our streams and the volume, and then the temperature coming in versus our current temperature, and then our heat transfer coefficient divided by the density and the volume and the specific heat capacity. And then that dealing with the temperature that is occurring in each individual CSTR minus the cooling jacket that is in contact with each of those CSTRs. And then, of course, adding in the heat that is occurring in each CSTR from our exothermic reaction. And so that's why we're adding that in here, because it's an exothermic reaction. It's giving off heat. And so that is also playing a role in how our temperature is changing over time. So these have been derived. And so let's go ahead and bring those equations in. And we're going to have to make some adjustments with what we initially coded out to match how it's changing with respect to time for each CSTR. Now, because the equations, the differential equations are the same, we're just having to split it up and track how it changes with respect to time for both concentration and temperature for each CSTR. What we can do, though, is take the initial parameters that we set with the equations that we derived previously. But the things that need to change here are, one is, let's go ahead and split up our array of values here so we can break this up into 2 sets. And what we're going to do here is place the first 15. So what we're going to do is index. And so what we're saying here is from the beginning, from 0 all the way to 15. The first set we want to track as concentration. Then the second array of values that we want to have here is going to be the second set, which is from 15 to the remaining, which is the 15 to 30, because we have 30 differential equations that we're solving for. And so we're going to put the first 15 as concentration, and then the back 15 as temperature, and how we're tracking this. And now a couple other things that need to change are, one is that the very first CSTR is what's receiving the initial conditions from the feed stream, but every respective CSTR is going to be different. So we need to have 2 separate functions here that we're solving for. So let's go ahead and specify what we're doing here. This one is going to be the first CSTR. There we go. And then this is going to be remaining CSTRs, 2 through 15. Okay, now let's go ahead and call this our initial for our parameters here. Now, in looking at this, this is receiving the initial concentration and the initial temperature, which is fine. But we need to index the value here, and indexing with Python starts at 0. And so we need to specify that as our value, as our indexed value for the temperature within the first CSTR. Go. Okay. TCO coolant, which I just noticed needs to change from 300 down to 290. Okay, concentration. All right, and our rate constant is going to change with respect to each CSTR, because as concentration is different and the temperature is different in every CSTR, that means our rate constant is also going to change respectively. So we need to index that value. I think we've got all of those initial ones there. Okay. Now for our remaining ones, the way we want to specify this is it's no longer the feed stream coming in, so we can't use that variable. What we can say is everything from the beginning, every previous CSTR, excluding the last one, because the last one doesn't pump into any future ones because it's the last of the line. And then we need to index the other way here, because indexing starts at 0. Well, we've already covered 0 on our first CSTR, so we're going to start at 1 here, meaning 1 is the index for CSTR2 all the way to the end of the line. And so we can do the same specifications for our rate constant and our concentration. And then the same thing with temperature, is it is receiving the temperature from everything that's come before it. I keep doing that, I think. No, there we go. And then the temperature within each respective CSTR that we are in. There we go. There's our cooling. Okay. Concentration. And there we go. Okay. Now we have two separate functions. We want to concatenate back these back together and bring the indexed values back together into a single array. Concat. There we go. Thank you, Google Laboratory, for helping me spell that. Okay. And now we need to specify. We have our DCAO. DT is what we called it. So we're gonna lump our concentrations back together, and then we're gonna lump our temperatures back together. Oops, probably shouldn't have done that. There we go. DTO, DT. There we go. Okay, great. So now we're going to go ahead and we've then put these, we've defined our right-hand side into our array of values with breaking it up between the first CSTR and then the remaining CSTR. So let's go ahead and simulate what this actually looks like as we plot it. So in order to plot and reveal our results, we have to solve the variables. And so let's go ahead and solve IVP. Use that tool now to solve all 30 of our differential equations, which are solving all 30 simultaneous differential equations. And then over the time span from 0 to t end, we are using our array of values, concatenate of what we got. Our two array values are CAO, our concentration of A, and then our temperature within each CSTR. The method that we'll use is redow. And then we want to be able to determine what each solution is, what the results are at each point that we ask. And so we need to use dense output here. All right, and need to close this in brackets. Rerun that. All right, well, as you can see, we have a change of location. I got kicked out of my spot in the library, ran out of the reservation time, and the little girl had reserved the next time slot, so I couldn't really say no. So here we are, different location, but the same problem. And let's go ahead and run this code. Well, a couple issues. One is, should not have put parentheses around this. And then line 106. All right, here we go. Forgot to put our rate constant with an index of 0 for our first CSTR. Let's rerun that. Let's rerun all of this. Okay, there we go. It liked that. Now, what we're going to do is plot this out. So let's go ahead and set up a variable for the number of integers that we're going to have in our time plot. Our time plot itself, we're going to name here, and we are going to go from 0 to t end, and this number of integers. There we go. Okay, now next up we want to split up our concentration and our temperature into two plots, otherwise it's going to get very messy. So let's go ahead and do that now. We need to name, let's close this out here. Name this as give this a variable name, so we'll call that results. Rerun that. And so now what we're going to do is we want all of our results to show along the time plot of everything we've got in our array of values, but we want to split this array of values, our 30 different order differential equations, into both. We want to show one plot for concentration, one plot for temperature. So let's go ahead and split that into two separate plots and data. Great. And we want to, actually I forgot to put in NP linspace so that we can have these properly spaced out on each point. Let's go ahead and get our subplots going here. All right, rows, we're going to have one. We're going to have one column. Great, so now we're going to take our array of values for I in range. The range is our number of CSTRs in series. What we're wanting to do now is, there we go. So now we're going to set our independent variable as our time plot. Our dependent variable, as the first one we'll do is concentration, second plot we'll do is temperature. So concentration, and the concentration is going to be starting with the first CSTR, moving all the way to the end. So we want to show that there, and then let's go ahead and give it a name. So for each iteration here, let's go ahead and name it concentration of A for each CSTR, row equals 1, column equals 1. There we go. And let's go ahead and there we go. Oops. Now, fig update layout. Let's go ahead and give it a width of 500, height of 500, and template equals plotly dark. Man, I can't type right now. There we go. The kids kept me up late last night. They kept waking up. All right, so what we're seeing here is in the first concentration of our first CSTR, it's moving, it's spiking up, and then it's moving up, but in decreasing measure as we go on down the tanks. And that would make sense when we consider the fact that even though they all start at the same concentration of A, at that 0.5 moles per liter, we have the inlet stream of 1 mole per liter coming in. And so the first CSTR is going to be the one that's receiving the most dosages of concentration of A. And so it should be the highest. And then as the reaction continues to occur, we should anticipate and see that reactant A continues to decrease over time, and that is indeed what we see. So the beginning tanks should have the highest, and it should continually drop off, because as each respective CSTR receives the previous concentrations, there's less and less amounts of A for each CSTR as it moves down, which is what we do see here. And so what we should anticipate for the temperature, because it's exothermic, when we go ahead and plot this next one, is we should see wherever there's more concentration, there should also be a direct proportion of increase in temperature. So where there's higher concentration, there should be a higher temperature, and then it should decrease accordingly. So let's go ahead and see if that's the case. Now we're going to take a lot of the same information, but we're going to make a figure 2 now for everything in here, and then just change the concentration to then show our temperatures instead. Okay, great, which is, it's showing what we were anticipating, which is where there's a greater concentration of A due to it being an exothermic reaction, we should also see there being an increased amount of temperature, which is indeed what we see. And as the CSTRs continue on, there's less and less A that is being reacted, and so there's less of an exothermic reaction taking place, and the coolant jacket continues to remain at the 290, so it continues to cool all the CSTRs, and as there's less heat coming in, obviously it's going to be cooler and cooler as time goes on. Thank you for being part of this video series to just see what happens with CSTRs in series and how both the mass and the energy balances change over time. Thank you.